Okay, that's 9 a.m. and we can start. So guys, today we're going to introduce Faraday's law. One of the, again, fundamental equations, and this is one of the equations from the set of Maxwell's equations, right? So at this point, after introduction of this law, we will have 3 equations out of 4 in the set of Maxwell's equations. You remember we started with the Gauss's law, that's the first one, then Ampere's law, the second one, and now there will be Faraday's law, right? So, but before I start introducing this Faraday's law, let's try to understand where we are in this course, right? Sort of global point of view. You remember we started with introducing of the world of electricity, and we basically laid down the foundation. I mentioned about this several times, where we presented basically all ways of finding electric field, the electric field, which is Coulomb's law and Gauss's law, right? And then we also introduced the electric force. F equals charge times the electric field, QE, right? So once you know the how to find the electric field, and once you know once you know how the electric field interacts with the material or with the point charge, that's the foundation. You don't need anything else. The rest, you should be able to derive the rest. You should be able to derive the rest. And then now what we've achieved in the world of magnetism. So we presented 2 ways of finding magnetic field, Biot-Savart law and Ampere's law. And in the previous lectures, right, and the recitation classes, we introduced the magnetic force, which basically describes how do those magnetic fields interact with point charges, and of course then as a result with the material. So we presented exactly the same foundation like we had in the world of electricity. So now we have, it looks like we have a full foundation in the world of electricity, and now it looks like a full foundation in the world of magnetism. It looks like life is great. We've achieved almost everything. Now it's just a question, it sounds like. It's just a question of application of that foundation for that problem, for this problem, for that problem, right? So we can retire and just enjoy applications. And I guess that was the feeling in the world of research, in the world of electromagnetism, I don't know, 150 years ago maybe, all right? When people felt like, okay, life is great, so we presented the foundation, so now it's just a question of applications. And at that great moment, Faraday came and ruined all this nice structure. So basically, yeah, he was a brilliant guy, brilliant experimentalist. He did tons of important experiments, and he found tons of important phenomena. Right? So he came and ruined all this beautiful castle of the world of electromagnetism. So basically what he did, he found some phenomena which couldn't be explained by all that foundation which was presented before and which I just mentioned to you. So he found some phenomena, and that couldn't be explained neither by Coulomb's law, or Gauss's law, or Ampere's law. Nothing of that could explain that phenomena. So what does it mean? It means that that foundation was not complete, and for us is not complete. You're commenting about the Faraday. Okay, guys, I will read the chat later, right? So it was not good at math, but he was great at experiments. Yeah, I know that he was not theoretician, right? Maxwell was a great theoretician, right? So basically, it means that the foundation is not complete right now. So it means that we need to add more equations to our foundation so that we can explain everything that we can observe around us. And yeah, Faraday's law was added in order to explain what Faraday observed, right? Okay, what he observed Of course, I will present, right? But first, let's sort of again introduce it from philosophical point of view. So you remember? Okay, now I'm sort of I am starting to present this Faraday's law. So you remember, right? In the past, recent past, we saw that any wire with a current produces magnetic field, right? We see the expression, we know the expressions because of our law can be used to find that magnetic field, right? And now let's ask a silly question. It's like a child, right, asking all kind of silly questions, but sometimes the questions are not very silly. And we also, let's ask kind of silly question, but is it possible to have a reverse situation? For example, can we produce electric current out of the magnetic field? And of course, yeah, it's possible. And this discovery, that's basically what Faraday's law gives us. This discovery changed the world. I want to say completely, not completely, but changed it significantly, right? Because it allowed us to produce electricity, right? And drive the whole industry using electricity. And we can also blame Faraday for a decline of Lowell, for example. Lowell was a prospering city, right? Full of textile mills, and then everything went down. It's all because of Faraday. We can blame him completely for the decline of Lowell. Because what? Before textile mills were built here because the river was needed, right? To drive those machines. And then when the electricity, then when we learn how to produce electricity and how to drive those machines, right? So then there was no need in the river, and industrialists moved all these mills to the south, right? Closer to the cotton plantations, right? Closer to a cheaper labor, right? Far away from the unions, right? Which demanded too much, right? As a result, all these cities went down. The life in all these cities went down, right? Well, it's all because of Faraday. Okay, anyway, and now let's actually present the what he observed, right? What he observed. Okay, usually I would bring the demo, right? But now I can use what I have in my apartment, right? Okay, so if you take a solenoid, basically a coil, right? You remember I used this already often. I used it often. All right, and attach it to a galvanometer, basically sort of like a voltmeter, which allows us to detect current, right? With the proper option, voltmeter with a proper option, right? All right, and then if you take a permanent magnet, okay, this is true permanent magnet, right? South, north, right? Again, I took it from my office. And all right, so if you start moving this magnet into the solenoid, again, you remember it is connected to the galvanometer. And if there's a current in the solenoid, then galvanometer will show it. If current, let's say, in a clockwise direction, the needle gets displaced or is displaced in one direction. If current is in the opposite direction, let's say in the counterclockwise direction, the needle will be displaced in the opposite direction, right? So basically it shows us that there is a current in the loop and also gives us information about a direction of the current. And then Faraday started playing with that, right? So if you take a permanent magnet and start moving into the loop, into this solenoid, right? If you move it, current appears. Needle gets displaced, let's say, showing that there is a current in the loop in a clockwise direction. So if you keep moving in, current is in the clockwise direction. Then, once you stop moving the magnet, although it's still exposed to the magnetic field, right? But once you stop moving the magnet, current disappears. The needle is in the middle, showing that there is no current right now. And then, if you start moving a magnet, but now in the opposite direction, out, then again current appears, but now current is in the opposite direction, in the counterclockwise direction. And again, if you stop at any moment of time, if you stop moving the magnet at any moment of time, current will disappear immediately. But of course, if you start moving again it out, current will be again in the counterclockwise direction. So if you move it in clockwise, out counterclockwise, clockwise, counterclockwise. But again, if you stop moving the magnet, if you don't move the magnet, current is not produced. And that's what Faraday observed. And this phenomena couldn't be explained by all those fundamental equations which we've introduced so far. It means that we need to start fudging. We need to start writing somehow a new equation which would explain this phenomena. Again, you remember all these fundamental equations, they cannot be derived. They just written by looking at observation and trying to match what we observe with the equation. And that's what was done with the Faraday's law. And again, we need to understand, like, so it's not just magnetic field, which, let me open the next slide. Oh, right, this slide, right. So basically that's what he observed, right. I took this picture, probably from the book, I don't remember exactly. And again, you see, it's not just the magnetic presence of the magnetic field produces the current. Because you remember, once you stop moving, so a solenoid is still exposed to the magnetic field, but current is not produced. So it's not just the magnetic field which is responsible for the magnetic field, for the current production. It's maybe some quantity which is related to the magnetic field. And that quantity must change in time because you must move. There must be some dynamics in order to produce current, right? So there must be some change in time of something in order to produce current. You see this. And of course, if there is a current in the loop, okay, let me take this out. If there is a current in the loop, it means that there is a potential difference, EMF, right? Because current, it's a consequence. If there is a potential difference in the loop, only then current flows, right? So that's what Faraday observed, and now we need to present this law. Basically, now we just need to understand what is this something that you have to change in order to produce current in the conducting loop, right? And that something, this something, is actually the magnetic flux. Magnetic flux. So, and at this point, I don't know how to say. So now let's present the new quantity, magnetic flux, or let's just review magnetic flux, because electric flux and magnetic flux are almost identical ideas, right? So basically, and we spend lots of time discussing electric flux. And the difference between magnetic flux and electric flux is just if you just replace electric field with the magnetic field in all those expressions. And you can recycle all those formulas and ideas from the world of electricity over here, all right? So, but strictly speaking, I should say, let's introduce the new quantity, which is called the magnetic flux. And that's our something. That's our something. It's a magnetic flux. Okay, so, and of course, we will cover it very fast. Right. First of all, again, idea. What's the idea behind the magnetic flux? It's basically number of magnetic field lines crossing a certain surface. You remember exactly the same words I said introducing the electric flux, right? So if you, for example, have, let's say, this flat surface, right, circular surface, and if it is exposed to the magnetic field, then of course there will be some number of magnetic field lines crossing this surface, right? So that's a flux, right? Okay, and in the simplest possible situation, if you have flat surface and uniform magnetic field, again, you remember we introduced the area vector A, which is perpendicular to the surface, but of course in this case it can point this way or in the opposite direction. Again, you remember you have, at this point you have freedom to choose the area vector this way or that way. Right. Again, you remember you need to use the correct angle between these two vectors, A and B, right? Position their tails at the same point in order to find the correct angle. And then for this simplest situation, flux, the number of magnetic field lines crossing the surface, can be found by the dot product, scalar product, but now between the magnetic field and the area vector. Again, this is solid dot, it's a dot product, scalar product, right? So if you write that explicitly, it will be magnitude of B times magnitude of A and times cosine of the correct angle theta, right? Okay, so exactly the same we had in the world of electricity, introducing the electric flux. And of course, if you have a more complicated situation, let's say magnetic field is not uniform, surface is not flat, in that case, of course, you have to integrate. Take a small patch, calculate the flux through the small patch of the surface, and then integrate it over the whole surface. That's how you can find the total magnetic flux through some surface which is not flat. Okay, so enough about the flux, because again, we spent enough time discussing electric flux, and here it's all the same. But now, what about the units, the SI units? Should we introduce the special unit for the magnetic flux? You remember, for the electric flux, we did not introduce a special unit. We just used whatever we saw in the formula, right? It was electric field times surface, right? So it's a newtons divided by coulombs times meters to the power of 2. So there was no special unit for the electric flux. What about magnetic flux? Do we need a special unit? Of course, strictly speaking, there's no real reason, but since this magnetic flux is used to describe electric current production, and current production is everywhere in our world, right? Of course, it makes sense to simplify life of all those technicians, electricians, engineers, right, physicists, right, because electric current is everywhere. And of course, it's all explained by the magnetic flux, by the presence of the magnetic flux. If a quantity is used a lot, it makes sense to introduce the special unit, so that people wouldn't have to produce every time. I have a flux of 5 Tesla times meter squared, or 10 Tesla times meter squared. It can be annoying, right? In order to simplify life at least a little bit, it makes sense in this case to introduce the special unit, Weber. Right. So 1 Weber, it's a 1 Tesla times meters to the power of 2. Again, just to make a life of people working in the industry slightly easier, to make life slightly easier. Yeah. Okay, so now we can say about sort of discrimination in physics, right? Again, electric flux, nothing, no special unit. Magnetic flux, here is the special unit for you. Not a fair treatment, right, of kind of quantities which are very similar. But again, since electric flux is not responsible for the current production, then no special unit. But here, Weber. Okay, so we're going to use it, of course, a lot. Okay, so, and now let's look at a couple of examples. No, I decided not to poll this, right? So it's reasonably easy. Usually students answer these questions almost 100% correctly. But we need to discuss it. So let's assume that we have uniform magnetic field. You see a bunch of dots. And of course, this uniform magnetic field goes all the way to that infinity. So there is no edge, there is no line where the magnetic field ends. And there is, you see, conducting loop, on some metal loop. And that loop is being dragged that way. What happens to the magnetic flux? Is the magnetic flux through this loop changes? Okay, changing. Is the magnetic flux changing or not? We have the simplest possible situation, right? Uniform magnetic field and flat surface. So we can use the formula, which is BA and times cosine of angle between them. So you see, 3 parameters are involved in the magnetic flux: B, A, and theta angle. And every time from this point, for several classes, we will be using these 3 parameters. Again, for whatever reasons, again, 3. Sort of like a trinity again now in the world of magnetism, BA theta. So let's look at them separately, one by one. Magnetic field, through the loop. As we drag the loop, magnetic field is not changing. So B stays constant. Right. Then area. Area of the loop, again, we're not distorting the area, right? We're not doing anything to this loop. So area of the loop stays the same also. A is constant. Angle, again, angle, of course, you can pick the area vector, for example, out of the board in the direction of the magnetic field. You remember you have freedom to choose the area vector out or in this case, no restrictions. So if you pick it out, angle will be 0. If you pick it in, angle will be 180 degrees, but anyway, it will be constant. So the angle is also constant. So all three parameters are constant, so of course the magnetic flux is constant. So in this case, magnetic flux is not changing. So flux stays the same. So in this case, no, flux is not changing. And we're going to analyze fluxes, again, for the next 2 or 3 classes a lot. So that's why I started with this simplest case. Okay, so now let's look at exactly the same system, but now let's assume that we spin this loop. We're not just dragging it in a certain direction, in that direction. Let's assume that we're spinning it around this axis, you see. So again, the same question. Is the magnetic flux through this loop changing? Again, so we have simplest possible situation. Uniform magnetic field, flat surface, so we can use B dot A formula, which is BA cosine theta. Again, that trinity, 3 parameters, BA theta. Let's analyze them one by one. Magnetic field still constant. Magnetic field through the loop. We're not changing it. Then area of the loop, it's still the same, right? Again, we're spinning, but we're not distorting the shape of the loop, so area stays the same. A is constant. But what about the angle now? Angle changing, right? So first, let's say area vector out, right, towards you. And then you start spinning it. Now, let's assume that we measure it relative to this direction. So now it's, let's say, 30 degrees, then 60 degrees, then 90 degrees, then 120 degrees, 180 degrees, right? So you see angle constantly changing, right? So then it will be get to 360, then 370, and so on. As you keep spinning, angle keeps increasing nonstop, right? So in this case, angle changing with time. So as a result, angle is changing. As a result, flux is changing also. Flux is changing. Okay, so in this case, flux is not constant. Right? Flux is changing. So again, as I said, we're going to analyze fluxes a lot. So, and now we introduce this very important quantity, magnetic flux, and now we can finally introduce the Faraday's law. Right? Again, it's the fundamental law, universal, timeless. You should be able to apply it at any point of the universe, at any moment of time. Anyone should be able to apply this. No restrictions. Right? That's what we mean by the fundamental law. And as a result, and it cannot be derived. So what can we do? We just can discuss phenomena, and we've already discussed it, and now we just need to present it, because again, it was written just based on observations, right? Okay, so I can tell only here is the law, tada, right? Enjoy it, use it, and let's see how it can be used. So what do we have here? You remember, if you have a loop. Right. Okay, in this case, it's just one loop. In the demonstration, not demonstration, in a description of a demonstration, we had a solenoid, but of course, solenoid is just basically a few thousand loops, just a few thousand loops. Okay, so let's assume that we have a conducting loop which is exposed to some external magnetic field. Exposed. Right, so there is a magnetic field, there is a loop, of course, there is a magnetic flux. Magnetic flux. If this magnetic flux changes in time, derivative in time is not zero. If that magnetic flux changes in time, then in this loop, somehow, mysteriously, there will be EMF produced. Again, you remember what is EMF? It's just a fancy word for a potential difference. There will be potential difference produced in the loop. And again, this is EMF over the whole loop, not just at one spot. It's an EMF in the whole loop. Sort of you can think of this as, I don't know, some small batteries uniformly distributed over the whole loop with the same polarity, with the same sort of orientation. Right? So it's a sort of uniform distribution of, but of course it has nothing to do with the batteries. In the batteries, EMF is produced, electric energy is produced from the energy of chemical reaction, right? So that physics is completely different. Here we're producing potential difference or EMF in a completely different way. Right? So if this magnetic flux changes in time, then EMF is produced. And since this is a conducting loop, so if there is an EMF, of course, there will be current flowing in this loop, induced current. Right. Okay, so this is Faraday's law. It looks very simple, right? Okay, so this is the, just I copied and pasted from the book. So EMF induced in the circuit is equal to the rate of change of the magnetic flux through the loop, through the circuit, right? Okay, and again, if you open it up, if you write explicitly the expression for the flux, like what we've done in the previous couple of slides, right? So it's a B, A, and cosine of angle, and the time derivative in front of them. So you see, in order to understand, if we're going to produce EMF, you just need to see, are there any quantities changing in the flux? If B is changing, of course, the EMF will be produced. If A is changing, then again, EMF can be produced. If angle is changing, again, EMF can be produced again. So every time we will be analyzing these three quantities, B, A, and the angle. So like in the demonstration which we discussed at the very beginning, so if you have a loop and you move the permanent magnet in this case, the major parameter which is going to produce EMF is the magnetic field. Magnetic field is getting stronger through the loop. So B is changing in time because you move the magnet closer and closer and closer to the solenoid. Right at the very beginning we discussed, of course, in this case, changing in time magnetic field is going to produce EMF, and as a result, current, you see current, induced current is going to flow in the loop. Second situation, right, uniform magnetic field. And let's say this is our conducting loop, and now let's assume that we spin it. Okay, in this case, angle theta changes in time, right? Angle changes in time. And of course, as a result, in this loop, there will be EMF produced, potential difference, and current will flow in the loop. In the last situation, what if area changes during your processes? So let's assume that we have uniform magnetic field, and there is a loop. And now let's say, for example, you maybe change the temperature, and as a result, let's assume that this loop is shrunk. So the area gets smaller. Let's say first loop was of this size, and then the loop went down to this size. So now area changed. Area changed in time, and as a result, in this loop, there will be EMF produced, and current will flow. Right? Current will flow.
Professor?
Again, guys, yeah.
I have a question.
Yeah.
If the current in the current loop was stopped, would it continue to spin because of the induced current?
Okay, your voice kind of was up and down, so the signal was not. Can you repeat it again? Maybe I will understand this time.
What would happen if the current loop lost its current?
Lost its current? Okay, I'm not completely following, right? So of course, current will be only over the period of time when you change something. Once you stop changing that, current will disappear. It's like when I discuss, at the very beginning when we were discussing what Faraday observed, right? So if I move magnetic, or if I move the permanent magnet in this case, I'm making magnetic field stronger. If I keep changing, right? So then current will be produced. Once I stop moving it, once I stop changing magnetic field, current will disappear. I'm still trying to understand the question, right? Is this the answer? Or you meant something else?
I think so. What I was wondering is if you had a loop with an induced current that caused this EMF to be produced.
No, no. Current is the consequence, right? So first of all, so you have a loop. If flux is changing, then EMF is produced, and then as a result, current is produced. So the sequence, you broke the sequence. So first, changing magnetic flux, then EMF is produced in the loop, and then current is produced. Okay, now,
Okay.
okay, is
Yes, thank you.
that was the question? Okay, okay. Right. Because when in your question, I heard that you broke the sequence of the events, right? So that's why I immediately decided to correct it, right? Okay, so first, changing in time magnetic flux, then as a result, EMF, potential difference is produced, and then, of course, if there is a potential difference, of course, current will flow, because that potential difference will start dragging electrons through the loop, and that's what current is. Right? Okay, so that's the correct sequence. Okay, so now, three possible situations, and again, as I said, we will be playing with these parameters for the next 2 or 3 classes. And now, again, it's the same law. I just started a new slide. So we have here minus in front, right? Whenever I see minuses, especially in front, they made me feel nervous, really nervous. Because it means that I need to look carefully what's the meaning of those or that minus. Because it means that something you have to take care of properly, right? Otherwise, something might go wrong. So this minus gives us a direction of the current flowing in the loop. Of course, direction of EMF as well, right? So this minus gives us direction of the current if it's flowing clockwise or counterclockwise, right? And dealing with this minus in order to find direction of the current is not very pleasant experience. So people didn't like it. And of course, if you don't like something, of course, sooner or later you will find a way of dealing with that in a slightly different way, more pleasant way. So that's what researchers did also a couple of, maybe 100 or 150 years ago, right? And Lenz came up with a nice rule. Although it's presented as the Lenz law, but now my attitude towards law, it's a Faraday's law, it's something fundamental, Gauss's law, but this is a very nice, elegant rule. Again, it's just my personal opinion, right? But most of the books, they present it as a Lenz law. Law, I usually prefer to use only for something which is really fundamental. And this is very nice, elegant, and actually I like this rule, but it's still, for me, it's just a rule. So minus will be replaced with this Lenz rule in order to find a direction of the current. As a result, now application of this Faraday's law, which we're going to do a lot, will be divided into 2 steps. First, we can find, for example, absolute value of EMF. Just forget about the minus, just find the absolute value of that rate of change of the magnetic flux. So it's a first step. And then the second step, we're going to use this Lenz rule to find actually a direction of the current, direction of EMF. All right. So we're going to use these steps almost in every examples, right? And of course, in your homework, you're going to do it. All right. Okay. So now Finding this absolute value is just nothing but just a little bit of algebra, or not algebra, calculus, a little bit of calculus, right? So nothing that can be discussed over here. We will just have to do it for each particular case. But lens rule, what is behind this lens? Let's introduce this lens rule. So here I just copied and pasted what book wrote about this lens rule. And whenever I read it, it doesn't give me much. Right? Very often I feel like I'm reading, I know some bank conditions when you borrow money or something, right? When I can barely understand anything, right? So if you want, you can read it. Let me introduce this lens rule in a much simpler words. But of course, it will be longer, right? And I'm going to present it in several layers. First, kind of on a very shallow level, sort of philosophical level, then a little bit deeper, and then eventually I will present the whole lens rule, right? So it will take us maybe like 5-10 minutes to present this lens rule. So first of all, let's present it on a very shallow level, again, sort of like a philosophical level. Any system in the universe doesn't like changes. Just 3 hours ago, I had a full confirmation of that statement when I was trying to wake up, right, at 6 a.m., right? It's my body wants to sleep, but I had to somehow force myself, right, to get up and start prepping for the classes, right? So my system, as part of the universe, doesn't like changes. And of course, in that case, was the changes in the state of sleeping, right? Or, for example, another example, and I'm sure that you struggle with the same problems in the morning. Another example, right? So Newton's first law. You remember Newton's first law in Physics 1? So if you have a point mass, right, which travels in a certain direction with a certain speed, this point mass is going to travel in that direction with that speed forever and ever. Basically, the system, the object, the point mass by itself doesn't want to change the state of motion, in this case, state of motion. So if you want to change the state of motion of this mass, you need to apply some external force. If you want to accelerate it, you need to push it in the direction of motion. If you want to decelerate it, you need to push it in the opposite direction. If you want to change direction, you need to push it perpendicular, for example, right? So again, by itself, system, point mass, doesn't want to change its state of motion. So again, as I said, any system in the universe doesn't like changes. So now our system, our loop, which is exposed to the magnetic field, what our system doesn't like, right? Our system doesn't like changes in magnetic flux. Changes in the magnetic flux. The system, the loop, wants to keep the magnetic flux as constant, as steady as possible. So if flux, for example, if flux increases, right, you remember we have a loop exposed to the magnetic field, so there is a magnetic flux. So if that flux, okay, this flux, right, if that flux increases, the system doesn't like it. And as a result, it will try to suppress it, try to suppress the flux. So the system in this case behaves like a rebel. It rebels. It's like it behaves like a Che Guevara. You remember that famous rebel, I think it was during the Cuban Revolution, I think, right? And students in 70s liked him a lot. They used to wear a T-shirt with his face, right? So the system behaves like in that way, right? So it tries to suppress the growth of that flux, right? Because the system doesn't like changes. So it's one case. Of course, the second case, what again, if we have this magnetic flux and this magnetic flux, right? And now let's assume that this flux is dying. So it's going down through the loop. For whatever reasons, we will see which reasons can be. So in this case, again, system doesn't like the fact that flux changes. In this case, the flux is dying. So the system will look at this, again, you're changing, right? I don't like it. In this case, the system will try to support dying flux. Again, how we will see. So in this case, the system tries to support the dying flux. And so in this case, system behaves like a, Florence Nightingale during the Crimean War, right? Supporting dying people, right? So, oh, you poor thing, you're dying. Let me help you. You will suffer longer, right? So in this case, yeah, the system will try to support dying flux. So again, you see, system doesn't like changes. Flux is growing, system tries to rebel, tries to suppress it. Flux is dying, system tries to support it. System wants to see flux as constant as possible. Right? Okay, so now that's the first level of Faraday, not Faraday's law, Lenz's rule. And now let me introduce the major players of this game, and then finally I will present the whole rule, right? And we're going to practice it. It's very straightforward, right? So players, again, electromagnetic players. Of course, the major player is the loop, right? But that's mechanical. Where I want to introduce electromagnetic players. So the first player, of course, is the external magnetic field. So loop exposed to the external magnetic field, right? All right, so that's the first player. The second player, of course, there will be current induced in the loop, clockwise or counterclockwise, but there will be current induced. We're going to call that current the induced current. That's the second player. So magnetic field, then the induced current in the loop. Then the last player, if there is a current flowing in the loop, induced current, will that current produce a magnetic field? Of course, any current is going to produce magnetic field. And that will be our additional magnetic field, secondary or induced magnetic field, because this magnetic field is produced by the induced current. So there will be the third player, the induced magnetic field. So we're going to have three players. External magnetic field, which produces all this mass. Okay, I feel like I need more hands for demonstrations, right? Not enough. Okay, so we have external magnetic field, induced current, and that induced current produces induced magnetic field. So we have two magnetic fields, original, external, and then induced magnetic field. And there is a current, induced current, so three major players. And now let's finally present the whole rule, right? And again, two situations, flux is growing, it's the first case we will discuss, and then flux is dying, it will be the second case. So let's start. So we have we have a conducting loop made of metal, right? And external magnetic field, the first player in the whole game, right? So that's the original situation. And again, as I said, let's assume that flux produced by this magnetic field is growing. Flux through the loop is growing. Again, you remember philosophical idea, the system, the loop, doesn't like it. And it rebels. It will try to suppress this flux. In which way? It will start driving an induced current. You remember that second player, an induced current in the loop in such a direction. Right now, we don't know the direction. But the God programmed everything properly. So everything will be in the right direction. So the current will start flowing in the direction so that the induced magnetic field, you remember that last player, the induced magnetic field will be in the opposite direction to the direction of the external magnetic field within the loop. Why in the opposite direction? Because you remember the system wants to suppress the growing flux. If this flux is positive, for example, flux produced by the external magnetic field, then flux produced by the induced magnetic field will be negative. So positive flux, negative flux, of course, there will be some suppression of the flux, right? So the induced magnetic field, must be in the opposite direction to the direction of the external magnetic field within the loop. Why within the loop? Because we're trying, okay, not we, the system. The system is trying to suppress the flux. Flux is within the loop. What is happening outside of the loop? Who cares? The flux is within the loop. Right, so the induced magnetic field, in this case, will be that way. So now, once you know, again, as I said, I feel like I need more, I need more hands, right? Like Kali with many hands, right? Right, so now, once we know the direction of the induced magnetic field, we should be able to find direction of the current, and that's what we need. Direction of the induced current. Because this magnetic field, induced magnetic field, is produced by the induced current. How can we find that direction of the current? Right-hand rule number 2. Okay, let me drop this external magnetic field now because I don't need it. So now, once I know direction of the induced magnetic field, it's enough. Now, right-hand rule number 2. You remember, which we used for to find direction of the magnetic field lines. But now we are going to apply that rule in the reverse direction. We apply that rule to find the direction of the magnetic field if you know direction of the current. But now we know the direction of the field, magnetic field, and we need to find the direction of the current. So you see, it's the same rule applied in the opposite direction. Okay, so magnetic field is that way, you see. So I need to curl my fingers to match this direction. You see, direction of the magnetic field is into the loop. So I have to curl my fingers like this to match that direction. So I have two options, either this way or that way. If I position my fingers, my hand like this, then direction is obviously wrong. The marker is in, but my fingers are out, so I have to position my hand like this. And then my outstretched thumb gives me direction of the current. So the same right-hand rule. Of course, you can say, how come that you use right-hand rule, which was used for a straight current? How come that you use it for the loop? Let me justify that. Basically, we applied the we finished applying Lenz's rule to find the direction of the current. Now let me just justify how come that I use the same right-hand rule for the loop, although we introduced it for a straight current. Let me use my ruler. Where is my ruler? Here. Okay, so let me justify that application of that right-hand rule. So if you have a straight current with the wire, straight wire with the current, sorry. All right, let's say current that way. And we usually use the right-hand rule to find the direction of the magnetic field lines. I would outstretch my thumb. I would outstretch my thumb in the direction of the current, and my curl fingers gives me direction of the magnetic field lines. And of course, we know that magnetic field lines form pure circles, right? Circles with the center on the wire. Right. Now, what if I slightly bend my wire? What would be different? What would be different? Of course, now my magnetic field lines are not going to be pure circles. They will be distorted circles, slightly distorted circles. But would it change direction of the magnetic field lines? No. Direction will be still the same, clockwise or counterclockwise. And I can still use the same right-hand rule to find the direction. Again, I can outstretch my thumb in the direction of the current, and my curled fingers are going to give me direction of those magnetic field lines. Of course, those magnetic field lines are not going to be circles. Now, if I distort my ruler, my current more to this shape, again, those magnetic field lines are going to be really distorted circles. But direction will be still the same. I can still apply the same right-hand rule. And if I keep bending and bending my ruler, right, of course, sooner or later I will end up with a circle. Of course, those magnetic field lines are not going to be circles, far from circles. But directions can be found still using the same right-hand rule. If I outstretch my thumb in the direction of the current, my curled fingers are going to give me directions of the magnetic field lines. That's why I use the same right-hand rule for the loop, because I just want to know the direction. Right? Okay, so after justifying application of that right-hand rule, now let's get back to the Lenz's rule and for the second case, what if the flux is dying? Okay, let me finish this and then we'll call it a day. Right. So again, let's start from the very beginning. So we have a loop exposed to the external magnetic field, red marker, external magnetic field. Let me hold you for 2 more minutes, right? Sorry. Okay, and now let's assume that the magnetic flux produced by this external magnetic field is dying now. Flux is dying, getting smaller. So now, again, the system, you remember philosophical idea, doesn't like when the flux changes. As a result, in this case, since the flux is dying, so the system will behave like a Florence Nightingale, right? Or you poor thing, you're dying, let me help you. Again, right? You'll suffer longer. So in this case, it will start, the loop will start driving the current in such a direction so that the induced magnetic field, blue marker, induced magnetic field will be in the same direction as the external magnetic field. Now directions are the same, because in this case, if this flux is positive, flux produced by this field will be also positive. Both fluxes will be positive, so as a result, this flux is going to support that one, right? So in this case, now we know the direction of the external, direction of the induced magnetic field, right? Now external can be, we can drop it, we don't need it anymore. So now once we know this direction, again, we can use right-hand rule to find the direction of the induced current, because this induced current produced this induced magnetic field. So now you see magnetic field that way, so I have to curl my fingers out of the loop like this. Because again, if I position my fingers like this, direction is this will be a wrong direction. So I have to position my hand like this. So within the loop, my fingers, directions of my fingers must match direction of the induced magnetic field. And then my outstretched thumb gives me direction, a correct direction for the current, induced current. So clockwise or counterclockwise. So that's Lenz's rule. We're going to use it next class. We're going to have plenty of examples. Right now, it might be confusing, but once you do it a couple of times, trust me, I went through this, right? It's quite straightforward. Okay, guys, sorry for holding you. Yeah, exactly 2 minutes, right? So next class, next week, right? So we will start applying this rule, and for probably the whole week, we're going to spend discussing this Faraday's law. Okay, thank you. If you have questions, ask me. I saw a few messages in the chat, but I cannot, sorry guys, right? If I start reading messages, right, then it takes time to get back to the lecture. Right? So far it doesn't work for me reading chat and lecturing. Right. Okay, if you have questions, ask. Otherwise, I will see you next week.
It's the sun. Every morning it runs through the sky. Golden